final afternoon session. So just to be clear, so we're starting a little earlier because we need to leave here at 5:30. This is Switzerland, so that really means 5:30. I'm still getting used to that. For the bus that will take us basically to the cable car that will take us up to the glacier. Okay, so really 5:30, we need to all be outside, sort of behind over there to take the bus. It's going to be a little chilly up there, so it's probably around freezing. You probably want some sort of sweater and the thickest coat that you have with you, okay? So, or the thickest coat that you don't have with you. Okay, so we'll start with one talk, first of all, by Yuan, and tell us a bit about the Lattice Schwinger model, and then we'll move on very quickly to the EPFL group, who will show us some preliminary ideas about putting gauge theories directly into Lattice. Yes.
So it's a very pleasure. It's a lot of pressure to be here, and I would like to thank the organizers for hosting such a nice workshop. And today I would like to talk about some ongoing progress with Grisha and grad student Eric, who's done a lot of work on this Lattice Schwinger model in all aspects, sharpen up my understanding of this model. So this work, my talk will be about the near critical behavior of the Lattice Schwinger model. Some of the things that we encountered along the way of building up tools to basically generally study different lattice Hamiltonian models in 1+1D and hopefully someday in 2+1D. So these lattice Hamiltonian models, the motivation of studying them because it's one of the few ways to study quantum field theory non-prescriptively, and in many cases it can give us a lot of different information than what we can learn from, say, a Euclidean lattice. So it's worth studying, and we're just with Grisha and Eric, we're building up tools such as exact diagonalization and DMRG to try to gradually attack more and more complicated models. And despite their powerful tools such as DMRG, there are still a lot of hard problems on lattice, right? So things are hard if we encounter some criticality, if we're doing higher dimensions, or if we're trying to reach continuum limit. So there's a lot of work to do, and today I'll focus on this one of the difficulties, which is studying the simulating the lattice model at the critical point. So, I think it's a consensus that near the critical point, things becomes very challenging, right? So the reason, in this RG flow picture, it's basically we have a lot more scales to worry about, right? So the correlation length diverges, and we have to include all of these extra degrees of freedom, which contribute democratically from all scales. But if we actually reverse the logic, if we actually look at the degrees of freedom that are governed, or the actual degrees of freedom we have to put in, they're very well approximated by a CFT, maybe with some a scaling breaking factors so basically, if we know a lot about the CFTs, in this case we do, we can use this thing use the self-consistency of the CFT to to come back and help us, and to make some of these hard problems manageable. And today I'll show a toy example of how this works in this framework of conformal perturbation theory applied to the 1+1D massive Schwinger model. So so our setup is identical to this staggered fermion setup that was discussed in this paper by Ross, Igor, Silvio, and Bernardo 2 years ago. So basically we have Majorana fermion coupled to a Yuan gauge field, and we discretize it and put it on a lattice, and we'll have this Hamiltonian written here. And the Gauss's law basically fixes all of the gauge degrees of freedom, so we basically just simulate, we're just computing this Hamiltonian as a spin chain with a long range interaction, which is very controllable. And there are some interesting, there are some matching parameters between the lattice units and the continuum field units. So one is this x, which is a reparameterization of the lattice spacing in the unit of the gauge coupling. And we have this mu, which is a reparameterization of the fermion mass. And this x will control the continuum limit. If we send x to infinity, then it's basically saying that the lattice spacing goes to 0 and we approach the continuum limit. And reversely, if x is very small, this limit is known as the strong coupling limit. And yeah, so what's done in this previous study is it is found that there's a very nice kind of a reparameter, kind of a shifting of parameters of the fermion mass, which gives us a better kind of continuum limit behavior. Yeah, and so what we know about the phase structure of this model is that at this theta angle is equal to pi, and the mass, which is roughly in this like shifted unit, roughly 1/3. So then we have we have a easing critical point. Yeah, and it's been studied a lot by different methods. Yeah. So if we look at the vicinity of this critical point, then so we can actually make this plot of the critical mass. So we fix at theta is equal to pi. So then at each x, if we take the fermion mass to be large enough, then we enter the broken phase, and along the way we have this critical point somewhere at somewhere at some value of m. Basically, it's so at x goes to infinity, we have this we have the continuum limit, where we basically only have two couplings. One is the m and one is the e, and some dimensionless ratio between these two parameters will be our critical coupling. And if we send x to infinity, then we're in the strong coupling limit. Then heuristically, if you just look at the Hamiltonian, then what we basically say is that we can treat this gauge interaction to be very strong. Then what we effectively have is that the gauge field is basically, so the gauge field can only take, so here theta is equal to pi, so it's L plus 1/2. So it's L will be fixed to be 0 or -1. And then we can throw away this term because it's a constant. And then we'll only have two terms, which is one is this fermion kinetic term, and the other one is the fermion mass term. And again, some dimensionless ratio between mu and x will be describing our critical coupling. So very heuristically, we'll say that mu is so the critical mu will be proportional to x, and if you plug it in to our continuum field unit, we'll see that the mass will go in this along this go along this line that's linear in 1/square root of x, which is the same as the lattice spacing. And in the the strong coupling limit is actually easier to study because we reach the thermodynamic limit faster because A is very large. So so actually the slope can be measured quite accurately. So I don't think there's any doubt that it should go this way. Yeah. But at the continuum limit, things become harder because A gets smaller, so it gets harder and harder to reach the continuum limit. And we also have this problem that measuring the critical point is already kind of difficult. So this determination of m star is quite challenging. When x is very large. So the way that I think the way that people kind of find how they find the critical point is through the finite size scaling. So we know that at the critical point, the gap closes. So if we simulate any models, we should see that so basically the mass gap is approximately 0 near the critical point. But a sharper way, which could be turned into a criterion, which is discussed by Hamer and Barber in their publication in 1980, is this finite size scaling. Because we're never going to reach infinite lattice, so our gap would never be 0. But if we have scale invariance, then the mass gap will go roughly as 1 over r. And r being the volume of the circle. Okay, we're doing periodic boundary condition. But yeah, it will be some volume factor. But the truth, okay, so in real world, since we're simulating things on with a lattice, we're never gonna see very clean this 1 over r behavior. Well, so we see it quite clean, but there will be breaking of this scale invariance because we have some lattice units or lattice scale set in. So if we don't quite reach the thermodynamic limit, then our mass gap will be polluted by 1 over r squared, 1 over r cubed, all these things. So that means if we measure the critical point using this finite size scaling, we will make error in the next leading order of 1 over r expansion. So this is why we still need to take n larger and larger and try to get a critical point measured accurately. As compared with if we didn't have any of these subleading corrections, then measuring the critical point would just be accurate at any finite n. Of course, that's too good to be true. So then this method was used, I think, throughout all of these years from 1980 all the way to very recently. And my claim is that since we know a lot about Ising CFT, we can use some of these knowledge about Ising CFT to kind of improve the scaling behavior in the sense that all of these subleading behavior of 1 over r will be controlled by some parameters in the CFT, which we can use to improve our fit. So kind of if we remove some of these subleading behaviors, then the critical point will converge by some crazy power of 1 over n, then the measurement will be much more accurate. And the claim is we can write down an effective theory of this model as CFT with some, CFT with some maybe emergent, a matching speed of light and some irrelevant perturbation. So the idea is that assume that we are right at the top of the critical point, but our volume is finite, and we have some UV cutoff because we're working on the lattice. Then these things will naturally introduce all sorts of irrelevant perturbations. And they're irrelevant because when we flow deep to the IR, we're still supposed to see the Ising fixed point. So then basically we could use our knowledge of the symmetries to kind of make a list of all of the possible irrelevant operators that can be turned on. And then we'll say that in our spectrum, all of the subleading in 1 over r behavior are captured by the conformal perturbation theory perturbed by this. And the rules is the following. First, none of these operators can be total derivative, because if you perturb any of the action by a total derivative, it's completely trivial. So basically, all of our operators that can show up will be quasi-primaries of the CFT. And there will be no spatial spin because we realize the rotation symmetry pretty well, right? So in the n goes to infinite limit, we're supposed to accurately restore the translational invariance. So none of the operators should have explicit dependence on the space. But that said, the operator can still have spinning. The operators doesn't have to be scalars. It can still be spinning, but all of the polarization should be on the time direction. So for example, I think this At level 4, we're going to have irrelevant information that is given by chi. So this linear combination of some level 4 Virasoro descendant that is not a scalar, but it's like some operators that are spinning, but the polarization is in the time direction. And on top of that, we have the TD bar. So these two operators will be our leading deformation. And yeah, then we'll also need to preserve the Z2 symmetry. So at theta is equal to pi, we're gonna have, so the UV model has Z2 symmetry. So none of these operators should be in the sigma family. And the last rule is that we have time reversal symmetry, which sends the Virasoro generator L to minus L bar. So this means that all of our operators should be should be symmetric under this. So there's no kind of like a time. So L like L3 plus L minus 3 would not be allowed because of this rule. I think it's like a -1 today. Yeah, there was a typo. So then we can just like write down, okay, so we made the list of all of the operators that can show up, and we'll just study the leading deformation from Ising. Yeah, so all of the other operators, so the leading deformation will just be TT bar and this level 4 descendants of the vacuum. And all the other operators are like at least, yeah, so at least down by another factor of 1 over n. Yeah. So then we can just parameterize all of our energy levels by their scaling dimension in the CFT and these two first order perturbation theory correction from the conformal perturbation theory, which is like basically it's one point function of TT bar and 1 point function of this level 4 descendants of vacuum. And so if we ignore these, the original thing would be like, okay, so the kind of thing that we try to use, which is similar to the finite size scaling, is this ratio of energy levels. So if we subtract everything by, so if first we subtract the ground state, and then we take the ratio because we don't know the emergence speed of light is. So we also need to cancel that out. So this ratio, if we take the first and the second eigenvalues, it should be the ratio between the scaling dimension of the epsilon operator and the sigma operator in the 2D Ising model. And it should be, sorry, this is a typo, it should be 8. Yeah. And then this is like ignoring all of the subleading corrections. If we do add subleading corrections, what we can do is that since we know that all of our energy levels to the 1 over n square or 1 over r square order should be captured by only by these two OP coefficients, multiplying their Wilson coefficients. If we take 3 of these ratios and and take some linear combination of them, then we can completely cancel out the dependence on these two unknown Wilson coefficients. So then we cook up this ratio. So it's like this original epsilon over delta sigma plus delta d sigma over delta sigma and delta d epsilon over delta sigma. It's like the beginning 4 energy levels, including the vacuum. So if we take these ratios, it's kind of like, then the only correction will be down by like at least 1 over r to the 1 over r cubed. And this ratio, this ratio is kind of model dependent. Any of the models that flows to Ising critical point and preserves Z2 and other like symmetries that we see here, like rotation symmetries, this ratio will work and improve. And okay, let's just try it very quickly for transverse field Ising model. First, this model is solvable, so we can actually check everything analytically to the order 1/n square. So all of these things match our previous calculation with, yes?
Can you remind me what n is here?
N is the number of number of sides. It's proportional to R. Yeah. And we also check that, okay, for example, if we just wanted to find the critical point using this ratio argument, so find the coupling G where the ratio goes to 8. Previously at 10 sides, well, so it's like a very small lattice, it's just like 10 sides. Previously, we already get like a very good measurement using like no correction at all. It's like 0.999. And if we use this correction, then we can basically improve it to 0.9997. So it's like this is like for the transfer field easing model, which is like a very simple and symmetric model. There's a lot of it doesn't have the subleading epsilon correction. That's why it's like converged so fast. Yeah. But this is like roughly the kind of improvement we're going to see. Things are going to be down by another 1/n factor. Oops. Yeah. Okay, so now let's apply it to the critical point of the the lattice Schwinger model. So here I'm showing these two plots at two different values of x. So at x is equal to 1, which is like very far in the strong coupling regime, basically the numerics is like very simple because the thermodynamics actually reached faster. So both of these both using the original ratio, just the delta epsilon over delta sigma is equal to 8, or the corrected ratio could work reasonably well. But if we look into the detail, the corrected ratio seems to be down by another factor of n. So it's like so this thing converges linearly, the other one seems to converge like quadratically or some higher power of n. And the two fit meet at the same point, roughly. And if we go to larger x, so we're further away from the strong coupling limit and closer to the continuum limit, then generally the numerics gets harder. And if we use the original ratio, then it's quite bad at like 20 sides. So at this stage, we're just doing some exact diagonalization. So 20 sides is already kind of like the limit where we can go. And well, if we study it harder, maybe we can go farther. But if you just run, say, some small cluster for multiple values of x for overnight, then this is basically where you can go. So it's like at the end value is still pretty far away from where it's actually converging to. But if we consider the improved ratio, it seems like the correction is much more mild. Yeah. So then we can just collect a lot of these plots and then try to fit each of the x, the m star to like n goes to infinity. And of course, things will have error. The way that we estimate the error is that we choose different fitting schemes. We can either choose to fit using the fitting model from like n between 14 and 20, basically 4 data points, or n between 10 and 20, just to give us a kind of like an idea of how things are still moving at this stage of n. And this is our kind of heuristic error bar, so take this with a grain of salt. Yeah, so this is not really proper error analysis. But it's pretty clear that things kind of like, so at larger and larger x, things very quickly becomes unacceptable. So for the original ratio, where this error becomes unacceptable is roughly at 0.4-ish. And then we can, yeah, with the improved ratio, we can basically double this and try to go to like 0.2. So this is the improvement, and then using these data, we can make a pretty accurate fit and get an estimate of the continuum limit critical mass, which is like a 0.3333 plus minus 3, yeah. sort of, yeah. So 1/3 is still in this region. We're not trying to like get really accurate measurement just using exact diagonalization. So to really say something seriously, we need to use DMRG. Yeah, but this is kind of like a flavor of how things would go if we use DMRG. Things are going to improve like this as well. Yeah. Okay, so then, yeah, so that's pretty much all of these like the technical fitting, and then using this improved measurement, we get like kind of a pretty accurate measurement of the phase diagram of the massive Ising model for like for different lattice spacing, different mass at theta is equal to pi. So we explicitly tested along, like, yeah, so explicitly tested this like line of critical point from the strongly coupled limit to the continuum limit, and basically it matches our understanding pretty well. At any point along this critical line, we can, at finite n, we can try to see how well are we measuring the CFD data, right? So one of the things we can look at is the spectrum. Of course, it will be very interesting if we can also look at, say, OP coefficients, correlators in the CFT, and that would be really awesome. Right now, we have the data for the spectrum up to, well, so we can like compute these things to as high as we want, but things gonna like converge poorly and like more and more poorly if we go to higher in the spectrum. And here we see that this fall off of yeah, so basically the convergence behavior is like roughly 1 over square root of 1 over n squared, which is basically agreeing with our error analysis. Our conformal perturbation analysis. Yeah. And then they converge to the scaling dimension of the CFT. Yeah. Okay, so yeah, so that's pretty much all I have to share. So the punchline is the conformal perturbation theory captures the near critical behavior, and then we can use this argument. We can use it to do a lot, and one of these things we can do is obtain a more accurate UV-IR matching, such as measuring the critical point of some UV model, right? And then, well, so things to do in the future is that, okay, so we don't just get the spectrum. It'll be much more interesting if we can use more of the real-time dynamical data, such as the matrix element in this quantum mechanical model, which is going to give us the 3-point function and 4-point function of CFT. And then, again, if we understand the conformal perturbation structure, we can use all of these to strengthen our UV-IR matching. Yeah. And to get rigorous results, we need to use the MRG. And right now, we're at this stage of like just building up the tools and doing a lot of the technical work to set things up. But there's one conceptual question we can ask, which is, which one is better, use periodic boundary condition or open boundary condition? This whole project, well, so this whole thing that I discussed is done in periodic boundary condition because we want to preserve rotation symmetry. But if we do understand things better in the open boundary condition, then maybe one day we can do a conformal perturbation study for open boundary condition as well, which is gonna give us a lot of like new and interesting structures such as deformation or topological order, all of these things. So it will be quite interesting to do it. And on the technical side, the DMRG on the open boundary condition will usually work much faster than the periodic boundary condition. So we'll get like benefit in that as well. And if all of these things work well, we can apply it to other models. Using the same strategy, we can test some of the numerically difficult regimes of, say, like two-flavor Schwinger model, 2D QCD, when there's like a lot of flavors, different gauge group, some hierarchy and mass. So all of these things we can test. And last but not least, we can maybe one day, if we do the lattice measurement like so well, then we can reverse the logic. These measurements tell us, so suppose we're near some critical point, then these data tell us kind of the finite scaling behavior of CFT with its own perturbation. And the perturbation will suffer from the constraints from the self-consistency of the CFT itself. And then the data is basically, yeah, if we put the data together with that self-consistency constraints, then we can maybe constrain the CFT as well, make some, yeah, some statement about the critical point of some random, of some unknown theory. And we can also maybe one day do this thing to other EFTs. Yeah. So that's it. Thank you very much.
Thank you for being so timely. Yeah. Maybe we'll move on for some questions while you guys set up.
Hey. Just, it's not a question, just in case people are wondering about where this Z2 phase transition comes from. If we just look at in the continuum limit, if we do bosonization, then the quasi-classical potential just shows this transition because the potential has a phi squared term and plus m cosine phi term. And then you see that for small mass, it's just a single minima, and for a large mass, it's 2 minima. But the precise transition, this doesn't tell you the position because it's strong coupling. So that's why one needs to do all this precision numerics.
I know you mentioned other CFT data. Have you thought about how the conformal perturbation theory would apply to, say, the entanglement entropy as a
I
different?
don't know. That's a very interesting question. Yeah. So, yeah, maybe the quantum information people will have something to say about it. But yeah, it would be very interesting if we have like some model of like how the entanglement entropy. So basically, for the CFT, 2D CFT, the entanglement entropy grows like a log of the space, right? But if we're breaking the CFT at some scale, then we're gonna see the breaking of this log behavior. Then it will be very interesting if we can kind of like measure these things. Yeah. Yeah. But yeah, I don't have a theory.
Presumably there are some twist operators and you will have some OPE with some irrelevant operators, right?
Yeah.
So it presumably falls under what you...
Yeah. So it's like
You have two twist
some
operators.
correlators of these twist operators. Yeah. Yeah.
DMRG, it might be significantly easier to convert a single ground state and look for its entropy rather than two excited states on top of it.
Yeah. That I agree. So if we just measure things for the ground state, yeah. So measuring some property of the ground state itself is much easier than measuring a lot of excited states. Usually for DMRG, yeah.
If there are no more questions, we'll thank again.
I would like to thank all the organizers for giving me and Barak this opportunity, and thanks for organizing this amazing conference. So we would like to talk about some problem related to pure Yang-Mills in Euclidean areas. We are interested in dimension, space dimension equal to 3 and 4. And so let me first say something about the motivation. For us, the main motivation is to understand the QC, the dynamics of QCD flux tubes in flat space. Namely the effective string theory. And so we would like to ask the following question. So can we say something already from UV point of view? in a sense, we can do some perturbation theory and make some prediction deep in the IR. And it turns out that ADS, putting Yuan in ADS seems to be a promising way to answer this question, because suppose you put Yuan in ADS, then we only have two scales. One is the QCD scale, lambda QCD, and another is the radius of the ADS. So there's only one dimensionless parameter you can tune. And then when when ADS radius is very small, then you expect it's in short distance, so you have a symptotic freedom, so you can trust perturbation theory. Then when radius is very large, much larger than lambda QCD inverse, then you are almost in the flat space. Then the phenomena of confinement start to appear, and the hope is you can interpolate continuously between r equals 0 and r equals infinity. And this is the dream goal. So let me describe the target we would like to study. So our setup is a Wilson loop inside the ADS, and we push the Wilson loop to the boundary. And so because there's no matter field, so you can make it infinitely large, and there's no dynamical quarks created, and then you at very large this radius, so in confinement there will be suit coming from the left-hand side of the Wilson line to the right side of the Wilson line. And in this regime, are much greater than lambda QCD, then you can write down some worldsheet theory. And which effectively describes the shape of the flux tube. And for the worldsheet theory in ADS, there's some symmetry which implies the. Let me first write it down. So we consider. Let me introduce the Poincare coordinates, dz squared plus d tau squared plus some transverse directions, and if you write down if you choose some gauge such that the worldsheet coordinates are z and tau, and then take the other transverse directions as variables on the worldsheet, then the theory will have some shift symmetry. Namely, you can shift xi to xi plus constant. So in flat space, the symmetry gives us Goldstone modes, which are massless. But in ADS, there's similar phenomena, but the conclusion is you will have some. So at the boundary, if you look at the observables staying on the Wilson line, and this gives some defect CFT, and in the defect CFT there will be some operator with protected scaling dimension, which is equal to 2. So this is the ADS version of Goldstone theorem, and the later Barak will gave some other argument saying there's some other mechanism to protect this dimension, and I would like to say since we have this some shift symmetry mechanism from worldsheet, so it gives some evidence that the string description of confinement is should be true.
Is this effective worldsheet theory supposed to be related to the string dual of whatever CFT?
Yeah, it's related to this worldsheet theory, just describing the flux tube, which connects the left side of the Wilson line to the right side of the Wilson line.
This is QFT in ADS.
QFT in ADS.
Yeah.
This is just the QCD string.
Yeah.
But the argument with this related to scaling dimensions to that worldsheet theory?
The idea is you have a worldsheet, and then if you choose some good coordinate, you can write this worldsheet theory as some scalar theory in ADS2. And in ADS2, you can argue if you have some shape symmetry, then at the boundary of ADS2, which is CFT1, you will have a scalar with protected scaling dimension, which is equal to 2. And there's also higher dimensional generalization. Then delta is equal to the space. It's equal to d space-time dimension. Okay. Yeah, I think I run out my part, so let Barak say something.
Okay, so maybe I'll start with the fact that probably Jiaxin was talking about taking the small r limit and continuously connecting it to the confining phase at large r limit, and a lot of you are probably suspicious because you remember a paper by Berkus, Tong, and Yankelovich, where they discussed the confinement phase transition in ADS. So the additional, I think we didn't say it so far, the additional piece of information is that this usual story is when we put the Dirichlet boundary condition on the ADS, and here we have some deconfined phase, some phase transition somewhere in the middle. Okay, I'm being very, and here we have confinement. That this is lambda QCD times R axis. So, and indeed, if you look at the spectrum here, you can see conserved charges over the SUN symmetry on the boundary, and then at some point you expect to develop. Once you start enlarging R, you expect at some point to develop a relevant operator on the boundary that is the symptom of this phase transition, or the cause of this phase transition. Now, what we are talking about today is instead putting ADS with Neumann boundary conditions on the gauge field. That means that we are setting if Z is the direction into ADS, we're setting FZI to be 0. So if you think about this classically, this just means there's no chromoelectric flux going out of ADS. So that's intuitively already a reason to believe that when the description is weakly coupled, you're going to get some description in terms of singlets. So it's not going to be, in whatever sense it can be confined, it's going to be confined. Or in other words, if you want, there is an expectation that for Neumann boundary conditions, there will not be a phase transition when you go to small radius. In addition, we can look at the spectrum. So now this is a lot of information. So maybe ignore the right-hand side of the board for now. So we start from the left-hand side. This is in 3 dimensions. So maybe some people don't see here. So what I'm doing here, I'm ordering the operators in the limit of small radius, where the description is in terms of just free Young-Mills fields is good, right? If I take the radius smaller, I'm basically in a small coupling regime, weak coupling regime. And on this side, I'm putting the operator we expect to see on the boundary once we use. Sorry, I can take it up a little bit. Should I commute them? Yeah. Thanks. So on this side, we are putting our expectation from just a theory of a Goldstone on ADS2, right? So this is basically a theory of a Goldstone on ADS2, like Jiaxin was saying. And on the boundary, we expect the dual of one Goldstone, one particle state in rest, the dual of 2 particle states at rest. Then we might have some these double traced operators corresponding to particles with momenta, 2 particles with momenta, and then 3 particles, and so on. So now, on the other hand, on the gauge side, on the side where the gauge theory description is valid, we have more particles, right? This comes from the fact that if we look at the Wilson line, on the Wilson line, we are inserting different particles, for example, F0I, that corresponds to a small displacement of the Wilson line, or we are inserting, sorry, let's say we're inserting 2 of these F01 displacement of the Wilson line in the one direction. The ordering also matters now, right? So we will have more operators corresponding to the fact that, well, for these I cannot really anti-symmetrize them, but in principle the ordering of the operators matter, which allows me to anti-symmetrize. So let's maybe just look at the examples that we have. So the lowest operator on this side, as Jiaxin said already, on the Wilson line we expect to have a displacement operator. So at least at very weak coupling we expect it to have dimension 2. It will be this F01. 0 is the direction along which we are setting the Wilson line, maybe I should say. And 1 is the perpendicular direction we are left with once we went to the boundary of ADS3. Now, you can write in principle a lot of operators, but you can use Bianchi identities and equations of motion to reduce them to this basically. This is the independent, linearly independent basis of operators. And we have 2 quantum numbers. We have 2 Z2s, that's parity in the spatial direction, and parity and charge conjugation together in the time, parity in the time direction together with the charge conjugation. So we can write the quantum numbers on both sides. The symmetries are symmetries on both sides. And we can imagine how it might look if we were able to extrapolate these 2 theories. So one thing we want to guess is that this dimension 2 operator that corresponds to displacement of our Wilson line on the boundary is protected. And maybe it has dimension 2 all of the way, right? It has dimension 2 on the 2 edges. So you might be tempted to guess that this is protected, also because of the description in terms of a Wilson line. And then we can try to match other operators, and we can try to do, one thing we could try, for example, to do is do perturbation theory on this side and try to see how it, whether we can extrapolate to something that looks similar to what we see on this side. This is one thing we could imagine. Now, in 4D maybe, let me see if I want to say anything else. So the different colors correspond to different quantum numbers. We just match the first operator on each side to the first operator on the other side. And yeah, maybe 4 dimensions is slightly more interesting because we have more operators. So here we have displacement, which is now a vector in the transverse O2 plane, transverse 2-dimensional plane. We have 2 quantum numbers corresponding to O2, and again this time reversal together with charge conjugation. And we again expect the displacement operator to just match to the dual of the Goldstone. But now we have more interesting operators. So here we have this placat that is kind of touching the Wilson line. Well, it's a bit hard to draw, but something like a placat that is touching the Wilson line like this, and is fully in the transverse plane. And that has the correct quantum numbers to match to a state of two Goldstones that already has dimension 5 on this side. Now, there is an expectation. Well, people who are familiar with the story of flux cube, that is the subject of the workshop. So, people who are familiar with the story know that from the lattice and from various arguments, we expect to see an axion on the 4-dimensional flux tube, so an axion resonance. And if this picture would be valid, then you'd expect that the line starting from here, extrapolated through many near crossings with other multi-Goldstone state, what from the right side can be interpreted as a multi-Goldstone state, should asymptote to a linear curve here that corresponds to for which the slope corresponds to the mass of this axiom. So these are different things one might hope to see from this type of picture. Okay, I don't know. So yeah, maybe another. So if we look at the two edges of this picture, the edge where we have 3 goldstones and this edge where we have just 3 young males, they might seem pretty similar because these are free theories, but they have one very important qualitative difference. So when we compute correlators in this dual series of free goldstone, we'll get contributions from diagrams right like this, if this is a 4-point function that we're computing, and also the diagram where we have this U-channel contraction of the four free operators. Now this one does not exist on this side, right? Because on this side, this picture is basically Wilson line F01, let's say it's 3 dimensions. F01, F01, and F01. So so now because of the trace ordering, sorry, maybe we didn't say that we're at large N. That's a very, that's what happens when there are 2 speakers, but sorry.
What are these circles? Sorry, just.
I'm sorry. This is the Wilson line. Okay, this is the boundary of ADS. I'm putting a Wilson line on the boundary of ADS in some slicing of it. If you want, maybe it's less confusing if I just draw. Well, in the weakly coupled description, it's a Wilson line. In the strong coupled description, also a Wilson line. It's the boundary of the worldsheet. But maybe
shown this picture that just Shin drew where your 4 points are, right?
These would be, let's say, 4 points inserted on the Wilson line. Yeah, sorry, this is the, And then at weak coupling, we have color ordering because we're at large N. At strong coupling, we don't have color ordering. So somehow, this extra diagram has to emerge as we extrapolate from weak coupling to strong coupling. And of course, the hope is that it happens in a not too messy way. And you can really see, for example, you compute leading order corrections to this, and you already see this know the word in Hebrew. Okay.
So this is kind of a cousin of a statement that in flat space, when we look at the scattering, and at low energies it's pure transmission because it's Bogota, and at high energies one thinks about partons inserted in a string and they bounce back and it's reflection, right? So that's this color ordering story.
Right, exactly. This is, in some sense, this is what we are going for. We are trying to have a more controlled setup for this. Exactly, yes. So yeah, indeed, if you can think of the fact that we are not allowed to have this channel, or the fact that we have ordering on this boundary of the string in weak coupling, as the fact that we are allowing zigzags, they are not highly suppressed because you're at weak coupling. So the string can make more creative forms, and we expect to have. So this is part of the reason we have more states on this side. Some of these states are expected to be pushed to be very heavy because they include the string being folded in some way. Yeah, maybe another perspective that is useful for this, if we want to think of a string in small radius of ADS, this is not something we are accustomed to because also we don't have strong coupling, but there's a story by Alda and Maldacena about the leading anomalous dimensions of operators with large angular momentum that, in some sense, can be also applied in this case. If you're not familiar with it, it won't really help you if I. But okay, this is highly inspired by this. So we can write the ADS metric in this way. So ds squared equal to cosh squared rho dz squared plus p rho squared over z squared plus b rho squared plus rho squared p omega. Now this is ADS2. right? And this is the rest of the ADS. So the question is now, what happens if I think of putting these two? Now what I'm doing, I'm cutting a slice like this, a constant time slice of this. So I have the Wilson line piercing here and piercing here. This means that some flux is sourced from one side and supposed to go to the other side. Now if I use this foliation to think about this as one of my ADS2 slices here, and then I have maybe other slices going and foliating the rest of this surface. This is the spatial part of one ADS2 slice. Then you can see that this would be the row direction. And we can see that as we go to larger row, we get this warp factor here, right? There's a strong warp factor. This means that if we have flux originating from here and going to here, it will be pushed in by this warp factor, and we'll get some fat. Okay, this is very schematic, but we expect to get some fat string. And so whoever knows this story by Alden and Maldacena, this is a very similar line of reasoning. So for them, they have quarks that rotate very fast in ADS, and then when you go to a moving frame, you get this type of warp factor. For us, this is almost, you just need to write the ADS metric in this way. And here you see you have a warp factor pushing your flux inside. But now you might complain that what is the relation to QCD or to confinement? This might also be true for Yuan. And the difference between the two pictures, what we expect is that as we enlarge the QCD, the ADS radius, so if we enlarge the ADS radius, the string, the warp factor weakens, and the string is allowed to enlarge, right? So if I just put a Yuan theory, for example, in ADS, if we look at the size of the string, it should go something like this as I change R. It's the string size. Width is appropriate. Supposed to just go. Yes. Oh. Supposed to just grow. Now what we expect with confinement is that it grows, and then at some point we hit roughly R, which is 1 over lambda QCD, and at that point this flattens. So your string, the ADS continues to grow, but your string doesn't grow anymore. So this allows us some continuous transition between the small radius, where you have the string that basically, you can think of it as a string, it kind of covers ADS length. Of course, ADS is infinite, so you can still go outside of the string or something. And this picture at large radius. And this gives us some hope that maybe we can construct some effective theory on this ADS2, which is really a 2D theory. And then this 2D theory is supposed to interpolate between the two sides, where the other modes corresponding to the row direction, maybe we integrate out, and then we have KK modes of some higher masses. But of course, the mass is of order 1. But okay, here I'm being maybe a bit speculative, but if you go to this limit, here it's a free theory. So KK modes don't talk to each other, right? And when you go to large radius, of course, the KK mode are supposed to really decouple, because you just really have a 2D theory. So maybe somehow in the middle they are not so important, or maybe they are still decoupled. Okay, this is speculative. And so, okay, we described for you a framework where we have control over what observables we are interested in. At small radius we have perturbative control. At large radius we have a good effective theory that we know how to construct. And our hope is to find some observable that we can maybe kind of shoot from both directions and see that they go roughly to the same value. Maybe this is a modest hope that we have from this. Now we are looking for the observable. Maybe it's this, just the spectrum itself. Maybe it's the 4-point function of this lowest operator that we believe we can identify on both sides. That's still an open question. We can compute anomalous dimensional P coefficients. Maybe this is kind of tough perturbation theory, but in EDS, but can be done in principle. Okay. Maybe I'll stop. No. Maybe a few quick questions before we have the class.
So you want to try to bootstrap these boundary correlators on the worldsheet instead of flux tube S matrix bootstrap, kind of bootstrap, coming back to a little bit more like conform with
I was hoping someone will ask this because I can advertise another paper, but no. Yes, the bootstrap is quite weak. There's not a lot of assumptions we can put in. We can put the dimension 2 operator and maybe fix the dimension of this guy. Sorry, of 4 dimensions, maybe fix the dimension of this guy close to here. Yeah, I'm not. We should do this, but it doesn't seem to be very strong. Parallel, I'm trying to develop a way to insert nonlinear linearized symmetries for Wilson lines. So I'm hoping to
that would give power to this matrix.
that would be, and in some sense it might be easier to do this on this side. Yes.
What about the connection to things like DFL? Because now you have some weak coupling.
And then you might first get the Euclidean signature and then recreate the reference. This is
But this is Lorentz and one is
probably, yes.
Okay, let's thank the speakers one more time.